The objective today is to explain what the Intel manual says about real numbers and floating point formats. So this section describes how real numbers are represented in floating point format in x87, FPU, and all these instructions. So as a reminder, SSE instructions are an extension of the SIMD execution model introduced with the MMX technology. If I'm remembering correctly, this is just an addition to the instructions we can use that came out sometime in the 90s, I think. But here you go, here are some of those examples. We're not going to get too down in the details there. Just going to focus on the Intel manual here. It says, this section is going to talk about those floating point formats in using these instructions and Intel AVX floating point instructions. So in working with floating points, we could be using some of these instructions. It also introduces terms such as normalized numbers, that's not a big deal, denormalized numbers, biased exponents, signed zeros, so that's a mind bender, having a negative zero. And then it says nans, as in not a number. And what I've come to understand that to mean is just infinity, which is funny to think of a negative infinity to a positive infinity, but there you go. Readers who are already familiar with floating point processing techniques and the IEEE Standard 754 for binary floating point arithmetic may wish to skip this section, but we're not going to skip it because it's, though it's tempting, it's very interesting. So let's hammer down real numbers first. So as shown in figure 410, the real number system comprises the continuum of real numbers from minus infinity to positive infinity. Because the size and number of registers that any computer can have is limited, only a subset of the real number continuum can be used in real number floating point calculations. As shown at the bottom of figure 4-10, the subset of real numbers that the IA32 architecture supports represents an approximation of the real number system, and the range and precision of this real number subset is determined by the IEEE Standard 754 floating point formats. So I did do a ton of research on that, and we'll have a separate video, one with pictures too, if that's your kind of thing. But for now, you should know that the decision on how we represent decimal numbers, numbers with decimal points like pi, 3.14, and so on, that way we store them has become a standard. It was so complex that we needed to make it a standard. And it took a while, not until 1985 did we create this. Well, IEEE created this standard, and it's just called 754. So I've said a lot, let's get some questions here. What is a real number? And that's just negative infinity to positive infinity. I think asking you what a floating point is too simple, so how about I do this? What is the name of the standard hardware vendors will use to store floating points? So anytime you're creating a processor in memory and you want to store these floating points, it makes sense if you're creating the hardware for you to put this in the architecture to make sure it looks like this standard says it should look like. And we'll go a little bit into those details, but you'll need separate videos to maybe really wrap your mind around it. But in terms of what the Intel manual says, to increase the speed and efficiency, so that's really good to know, there is reasoning behind the craziness you're about to learn. To increase the speed and efficiency of real number computations, computers and microprocessors typically represent real numbers in a binary floating point format. In this format, a real number has three parts: a sign, to say positive or negative, a significand, and an exponent. So a picture's worth 1,000 words. This right here is considered a normalized number when we have a single digit and then the decimal with other numbers that follow. And you all, decimal people, are used to seeing it being times 10 to the 3 or to the whatever. So that just meant, you learned this in elementary school, since it's times 10 to the 3, you take this and you move it 1, 2, 3. So this number is actually the number 1,234, right? But this is kind of dumb. Why do we do this at all? We're supposed to be doing it to save space. So you can make that connection right away with computers. you're going to be saving memory by storing numbers in this way. But I mean, a number like this, you'd be wasting your time. And again, this is decimal. This is a better example over here. So 1.2 times 10 to the 5, we have 1, 2, 3, 4, 5 numbers that are representing 6 numbers total. So that's why I said this is the not dumb version. But here's the drawback. It says you lose precision. I could have an enormous number like this. And if I just do, 4 decimals, 1.234 times 10 to the 15, if I just move this, I would assume the rest are zeros, though as you can see based on this number, they are not. So that's life. There's benefits and drawbacks to designing things the way you design them. When the Intel manual says significant, that was the 1, 2, 3 number we're just looking at. But then the exponent, we were just looking at 10 to the 15. 15 is the exponent. 10 is the base. But we know that with binary numbers, we're talking about base 2. So let's just write that down. What base do binary numbers use when using scientific notation, I should say. And so here's your hint again. When you do something like this, this is scientific notation. Just not to confuse you, let's turn that into an 8. So we times by 10 in regular scientific notation that you might do in school in science class. But if we're talking binary numbers, you only get ones or zeros. And those will always be times 2, the 2 base. And then I can exponent that by however much I want, of course. I can go with 8 right there. So that's the format that they're talking about in the Intel manual. And I make this joke right here, one encoding to rule them all, because it says microprocessors typically represent real numbers in a binary floating point format. So that's the typical encoding. Now the sign is a binary value that indicates whether the number is positive or negative. You know that already. And don't forget, we could have negative values here. So instead of positive 8, if I did negative 8, instead of moving the decimal this way, I would be moving the decimal this way. Oh, and that looks so ugly. But if I move the decimal that way, now what we're looking at is actually a really small number. But that's the whole point, right? A negative infinity to positive infinity. So over here, they'll say that the significand has 2 parts, a 1-bit binary integer, also referred to as the j-bit, and a binary fraction. The integer bit is often not represented, but instead is an implied value. So that's crazy, but makes sense. Since we're talking about binary numbers, it's either a 1 or a 0, and we typically will never show a decimal number. Let's go with that. We'll never show it starting with a 0, because in this case, we would just put the decimal right there and get rid of that. That's the j-bit, and this is the fraction part, right? Okay, but we're storing all these in binary numbers. So the exponent is a binary integer that represents a base 2 power by which the significand is multiplied. Table 4.5 shows how the real numbers 178.125, that is in an ordinary decimal format, is stored according to that standard floating point format. The table lists a progression of real number notations that lead to the single precision. When you see single precision, just remember a 32-bit floating point format. And I'll just word the question like this: how many bits are in a single precision number? Or numbers? In this format, the significand is normalized. So remember what I was saying about normalized? That means it's a 1 point something, whatever it is. We're not going to go with a 0 point something. And we're also not going to go with like 2 numbers and then something. We're always going to have just 1 point, and then the rest of the numbers come after that. Okay, and that's for the single precision floating point format. The biasing constant is plus 127. But the exponent part, right, whatever you're raising it to the power of, this is going to need to be biased, and I'll get into that in a little bit. but it's so complex and you might need practice with it. It really needs to be another video. Today, we're just going over real numbers and floating point formats. If you could walk away with the format, I will give you the biasing information in another video. And at this point in the manual, they're just talking about single precision floating point format, because at this point in the manual, they'll usually show us the 32-bit stuff first and then go into the 64-bit when there is a difference, that is. But something for your notebook here, the biasing constant is plus 27. You should remember that. So what is that biasing constant in a single precision floating point value? And if you're wondering why I wrote these numbers right here, those are binary fractions. Let me show you a quick example. If I have one point, let's say 001, this is not 1.1. That's what I used to think a floating point would do, right? Like this being a decimal number, this is not that. But instead, what you do, this is the ones place normally, right? What you do is this is the 1/2's place and the 1/4. You see 2 and then 4 and then 8 here. So what is 1/8? 1 divided by 8, that's the decimal value of 1.125. So therefore that number is 1.125. And along similar lines, if I had, let's say this, okay, so we know this is a 2, so the number is 2.5, because 1/2 is just 5, 0.5 that is. So that's why you see the fractions there, because that's how binary decimals work. That sounds so funny to say because the decimal point in English is called a decimal point. These guys actually use the term mantissa. So here's that figure they're talking so much about. I think these might be symbols for infinity. They just look funky. And I also don't know why these spaces are not even, but whatever. If you know the answer, please let me know in the comments or explain it to me, please. And now this figure just makes me question my knowledge of J-bit. I thought I knew what it was when reading up here. Because see right here it says the integer bit is often not represented. And what's the integer bit? I thought it was this 1-bit binary integer. Well, there's just more research for me to do there. Let's finish up this video by looking, I did like this one. Let's look at real and floating point number notation. So see how these say binary right here? For it to be normalized, this always has to be a 1. So it's going to be a 1 point and then something. And then the e, of course, is exponent, just like before. But this is using base 10, or using a 10 to raise to the power of 2 in this circumstance. Down here, they're using a base 2, and this would be raised to the power of, well, 1, 2, 4, so that is the power of 7. So I wonder if we just go over here and move this decimal over by 7 places, since we're in base 2. And up here, these two are the same numbers. That just makes logical sense. But down here, it gets funky when they say biased exponent. So I noticed that this number was the exact same as this number right here. So you're raising to the power of a biased exponent. So I'm trying to figure out the connection between these two and this. But for the sake of this video, we'll just end it on that. That now you know the format for the floating point numbers. You see it right here. You'll learn more about how the format works in the next video. And then you just understand what real numbers are. And even what that term normalized means. Which will actually be a big part of the next video. So thanks for watching, and I'll see you in the next one.